Welcome to section 1.6, differential equations. The whole topic in this section is about making the proper substitution to turn your problem into something that's easier to solve. In problem 1 here, we have our differential equation, and it's not readily clear what you might substitute. So let's start to clean it up and maybe something will pop out. So let's see. Here we start off. I'm going to divide both sides by x plus 2y. All right, so y prime is here by itself. I'm noticing I've got an x here, and so I've decided I'm going to factor an x out of the top and the bottom. So by doing that, these x's can cancel, and I'm left with terms of y over x in two places. So that suggests that maybe we could make a substitution, and so I'm going to let v be y over x. If I let that happen, then certainly vx is equal to y. And if I differentiate both sides, on the right I get dy dx, on the left I use the product rule, and so now I'm going to use that information and substitute for y prime, and I'm going to rename these v, and so that leads us to this particular line. Alright, so looking at that, I move the v to the right, so minus v. Now I'm going to try to get a common denominator to combine these terms. All right, so cleaning all that up, collecting up like terms. And I see there's a 2 in common, so factor a minus 2 out of it. All right, now looking at that, what do we have? Well, I see an x, and I see a bunch of stuff that only has v's in it. So I should be able to separate this. So multiply by the reciprocal, bring it to the left. The right has a minus 2. This is an x, so now 1 over x on the right. And so we're going to integrate both sides. Now the right side is easy. This is minus 2 ln absolute value of x plus c. The left, if you look at it a little bit, if you let u be the denominator, the bottom part, the derivative of that bottom part is the top part. So I can use all of that to make a substitution, and I'm simply integrating 1 over u du, which is ln absolute value of u. And so now fill back in what's v. All right, so I need to get my hands on the inside parts. So I'm going to take e of both sides. We've done this previously. So e to the ln of something, I get it back. I'm going to push this back up on the absolute value of x. So when I get e to this thing, it's x to the minus 2. I'm going to get an e to the c, but I just recall that c. All right, so that looks pretty straightforward. Fill back in what we know about v being y over x. All right, so let's see what we can clean up here. If I multiply through by x squared, I would get this relationship. Or if I simplify this in a different way, we can get this relationship where x squared is there on the left. Okay. In question 2, again, it's not readily apparent what to do. So let's see. First off, I'm going to divide by x. All right, there's my y over x again. On this inside part, let's see. I've got the square root of x over this x, but this is the square root of x squared on the bottom, and this would be square root 1 over x. And so this term gives me my y over x again. So I let v be the inside part. Got it? Product rule if I differentiate on both sides. Substitute for dy dx right here. So that goes to there. This is v plus 4 square root of v. All right, so looking at that, let's see. What if I bring this v to the right? It would cancel, leaving me with 4 square root of v. But again, this stuff only has v's in it, so I can separate. So I'm going to divide by the square root of v. I'm going to bring the x to the right, so 1 over x, and then integrate both sides. On the left is easy for ln absolute value of x plus c. On the left here, I've got my power rule, minus a half plus 1. All right, so this fraction flips, and I get 2 square root v. Let's see, divide through by 2, so I get the square root of v. It would be c over 2, but I'm still calling this thing c. All right, let me square both sides to get v by itself. Now v is y over x, and multiply both sides by x to get my final relationship for y. All right, in question 3, all right, I got y prime is this stuff here, and it's being squared. So why don't I just let v be all of the inside stuff, and we'll see what happens. So the derivative of that on both sides, derivative of this is just 361. And so if I solve for dy, I get this relationship that I can substitute in on the left. All right, so bring the 361 to the right. All right, now looking at that, I'm noticing only these I can separate. All right, integrate both sides. I'm integrating 1. That's easy. That's x plus c. This 361 is a nice number. It turns out to be 19 squared, which is exactly what I need when I integrate to get the inverse tangent. So here's our basic rule, if you've forgotten the rule for the inverse tangent. All right, so looking at that, well, what do I know about v? Well, here was my substitution for v. I'm going to multiply through by 19. I want to get the inverse tangent alone. I'm going to take the tangent of both sides. All right, that'll get my hands on the inside stuff. Multiply by 19 to clear this away. I'm trying to get y by itself. And so finally, with a little work, we have solved our differential equation. All right, in question 4, we want to show that this particular kind of differential equation is called exact. Normally, differential equations of this form look like this format, and it's exact if the partial derivative of the m, which is the stuff in front of the dx, is exactly equal to the partial derivative of the n, which is the stuff in front of the dy. So remember, when I take the derivative of m with respect to y, all of the x's are treated as constants. So the derivative of 8x is 0, and I simply get the 3. The derivative of the n with respect to x, all the y's are constants, so that goes away, and I get 3. So yes, the partial derivatives do match, and so it is exact. So I'm looking for, when it's exact, a function of the form that's f of x and y is equal to c. So what do I know? I know that the derivative of this function I'm looking for with respect to x is m. All right, well, here's m, and so to get f, I would integrate this, and I get 8x squared over 2 plus, so this is a constant, so I get a 3xy. But there may have been something on the end. Well, you might say, well, why isn't it c? Well, because remember, if I'm taking the derivative with respect to x, anything with y's were treated like they were constant, so it could be an h of y. So that gives me my first look at what capital F would look like. But I know the derivative of f with respect to y is supposed to be n. And so if I differentiate this with respect to y, the x's are constant, so it goes. I get a 3x, and I get the derivative with respect to y, which is simply h prime. And this being n says that h prime is 8y. And so if h prime is 8y, then if I integrate with respect to y, I get 4y squared plus c. So now, here was my look at capital F. So plug in what I just found out about h of y, and so I get my relationship for f of x and y. Or you could write it in this particular format. All right, so looking here in question 5, we have a second order differential equation here. And so we look at it in this form. I'm going to try to reduce it down to a first order. Solve the first order and then continue going. So I'm going to let p be y prime. Well, then the second derivative of y would be the first derivative of p, which is the derivative of p with respect to y dy dx. But we have decided to call this term p. All right, so if I plug this in, then y double prime is dp dy times p plus 121y is 0. All right, so if I move this to the right, all of this stuff simply has y in it. All right, so I'm going to move the dy to the right-hand side, integrate both sides because I've separated it. And so I get 1/2 p squared equals, all right, integrate this, y squared over 2. So these would multiply through by 2. And so I get a relationship for p. All right, well, let's see. Looking at that, let me clean that up a little bit. What if I took out of this thing a 121? Why 121? Because I know the square root of that. All right, so I'll do that. I'll get the y squared alone. And then I've got c over 121, which I'll just call some constant k squared. All right, now p was y prime. All right, so now looking at this is p dy dx. All right, so I've got all this stuff. So this looks separable. So bring this in the denominator, leave the 11 there, dx. And so I get 11x plus c when I integrate the 11. This particular thing that we were manipulating is an integral you may have forgotten, but it's the inverse sign. And so to get my hands on the inside, I take the sine of both sides, multiply by k. All right, and then I want to mess with this thing to get it in a particular format. So I'm going to expand this using the sign of the sum of two angles. Sine of the first, cosine of the second, cosine of the first, sine of the second. All right, so now let's see all of this stuff. This k cosine of c, I'm going to call that a. K in this part, I'm going to call b. And so we finally get to format that our solution is a sine of 11x plus b cosine of 11x. All right, in question 6, we're going to show that if I do this substitution, it's going to transform this differential equation into a separable one. So let's see. Here's v right here. So if I isolate the y part, by is this stuff, divide through by b, all right, so I get a 1 over b times this stuff. And so if I differentiate this with respect to x, all right, so dy dx, 1 over b plays no role. This is dv dx. Differentiate this with respect to x. I get an a, and the derivative of this as a constant is 0. Okay, so I've got this part here, this part here. And so, what is dy dx? Well, that's this stuff. F of v is on the right-hand side. And if I get the dv dx alone, what I see is that this does become separable because I've got all the v stuff on one side and one dv on the right. So it is separable. Now, in our last problem here in this section, we're doing something that comes from the Bernoulli equation. It's a general substitution, comes up often in physics, physical chemistry, and engineering. So, we've got this Bernoulli equation here, and they're saying make the substitution v equals y to the 1 minus n. And if we do, it's going to transform it into something that looks like the following. Well, what is the following? Well, look, this is a first order. Here is a new p of x. Here's a new q of x. And so we know how to solve that by our integrating factors. All right, well, let's see. V is this, so dv dx, differentiating this by the chain rule, 1 over n in the front, 1 minus n minus 1. But 1 minus 1 is 0, so I get a y to the minus n. And so, comparing the right-hand side with the left-hand side, dv dx is, and I just rewrote this as 1 over y to the n, and so I get dy dx is y to the n over 1 minus n. Okay, that seems, hold that thought. We now know something about this term, which will go in up there. We need one more fact though. Let's see. V is y to the 1 minus n, but really that's y to the 1 times y to the minus n, and I'm going to rewrite y to the minus n as 1 over y to the n, and so I get that y is Vyn. All right, so let's see. Plug in what I know about dy dx. Plug in what I just found out about y. All right, so that's there. Multiply both sides and all terms by this reciprocal. And so I get dv dx. So multiplying this guy in here, the y to the n goes. So the y's are gone. And on the right, the y to the n would cancel. And so we get a first order problem in terms of v that we can easily solve by our integrating factor.